University called Central School of Engineering. He has done PhD in Computer Science and Engineering from Indian Institute of Technology Indore in 2018. His current research interests include quantum computing, inspired neural network learning algorithm, pattern recognition, hybrid neural network, and deep learning. He has published various journal papers, including IEEE Transactions, SCI Index. He is the reviewer of the Neural Processing Letters, Soft Computing is Springer, IEEE SSCI, InterScience Journals, and many more. He is also working in some projects in collaboration with the University of Technology, Sydney, IIT Indore, CSIR CD Plani, and CDEC Pune. Prior to joining MU, he worked as an assistant professor in the Department of Computer Science and Engineering at JP Institute of Information Technology, Noida. We welcome you, sir. Over to you, sir.
Thank you very much, ma'am. So let's start. So good morning, everyone. So as you can, my screen is visible?
Yes, sir.
Okay, fine. So as you can see, you are listening many lectures on quantum computing. So there may possibility something may be repeated, but this is required. This base is required for whatever I am discussing today. So if you see my topic is quantum machine learning. So quantum machine learning, if you are expecting that we will discuss about all the algorithm of quantum machine learning, it is not feasible in 3 hours. So for better understanding of this topic, we can divide this quantum machine learning in 2 parts, or you can say quantum computing in 2 parts. First is the quantum computing with classical computer. Whatever system you have, you can run normal quantum inspired program on your classical computer. And second, on actual quantum computer. So for actual quantum computer, there is a limited qubit computer available by IBM or Google. However, in this simulator, you can run to a particular extent bits or particular length bit programs. If we see this thing, first we will talk about this, then I will take something from this actual quantum computing, and we will discuss about the basic algorithm of machine learning, because each algorithm in quantum machine learning required a deep knowledge of its basics. For example, in this lecture, there may be possibility after this break, I will discuss about quantum K-mean. So in K-means, if you see, we will discuss some of the classical K-mean also. The core thing is distance calculation between 2 points. So for this, there is some knowledge is required of swapping of bits or some gates. But if you see support vector machine or some other machine learning algorithm, then you should have knowledge of how to find eigenvectors in algorithm in this quantum algorithm. So and it is very much difficult to explain this thing in 3 hours. Even anyone can explain in one day also or 2 days also. It is not very easy to understand this, because most of the participant may belongs to the this normal computer science area, and we don't have much knowledge about the mathematics behind quantum physics. So you also experienced this thing in the last few lectures, something which you are the speaker is speaking, you are unable to connect with the whatever you have studied. It's happened initially. The quantum computing take times. Now, if we talk about in the classical computer, so there is some algorithm which is inspired from this quantum phenomenon. For example, you have heard about the name of this genetic algorithm. So basically, genetic things or genetic whatever the actual genetic is found in the human body or animal body, or But inspired from that, we have made some program or some algorithm which can run on this our classical computer. So similarly, the first field which I will discuss about this quantum computing with classical computer, about something is inspired from this quantum physics. And second is actual quantum computing things, which we will discuss quantum K-mean. So let's start. So if I talk about the first thing, so here I will discuss quantum evolutionary algorithm. I will try to explain so that you something you understand in this 3-hour lecture. Okay, so these are the outlines. Hope it is visible. So these are the outline. So if we see, to understand this topic, first I will discuss some briefly about this quantum computing concepts. So you know about this classical physics law. So we have studied in our school time the Newton physics law. If we apply some force on some static body, then it will go in the movement or in motion. Okay, and if force and acceleration relation, similarly the action and reaction law we have studied. So these all laws are applicable on a thing which we can see on Earth. For example, if a car is moving, let's say a car is moving towards Agra to Noida, and it is at a particular point of some at the Gautam Buddha Nagar or just a starting point at 8 o'clock, and it is moving at the speed of 60 or 80. So after 1 hour, you can say that that car has been reached at that particular position. So the position of this car you can predict if you know its direction and its speed. But when you go at very atomic level, for example, at the electron level, when electron reside in some orbit, the motion of this electron cannot predict, or whatever the law we implement in the normal classical world, they are not implemented on this small tiny particle. Similarly, these law also not implemented or not applied on a very big particle like planets. So we will discuss about this thing. The quantum physics is all about discussing about the behavior of these tiny particle electrons and protons at atomic level and how we can use its power for the computing. Okay, we will discuss in detail. So at the atomic level, it is difficult. It is not possible to apply the law of classical mechanics. So they behave in a different way. For example, if an electron, let's say, if I talk about this single slit or double slit experiment, if electron is passing through a passage, then let's say some ball is passing through a passage, then this ball will directly collide to this position if it is not colliding at the edge of these slits. If I narrow down these slits, then this ball is not possible to pass. But let's say if I narrow down so much and I am, rather than some balls, I am passing some electron. So electron can pass from this passage. Now, general probability is we will say that the electron will collide at the front of this pass. But in the experiment, it is found that there is some probability, there is only some probability that we can find this electron at the just in front of that pass. It may be available here, it may be available here, it may be available here, it may be available here at this place also. If I close one electron or I see one electron in some particular box at different direction, so there is possibility that this electron can be found here, this electron can be found here, this electron can be found here. So there is only some probability by which we can say that electron may be available at a particular place. We cannot predict its position just like we do in the classical mechanics. So if at the same time the one thing is present at the more than one location, so you can understand benefit of it. It's mean if, for example, it's not exact example, but if a person is present at multiple place, so he can do parallel work, correct, with some probability. So there is a two main property of quantum qubits or quantum physics. First is the superposition and second is entanglement. How its benefit to the computing, we will see. So what is superposition? Before that superposition, we see how we define these bits in our classical computer. So let's say this is my memory, this is my RAM. And this is the width of RAM is 1, 2, 3, 4, 5 bit only. So if this is my RAM, and let's say there is a 1000 position, okay, from 0 to 999, and width is 5 means there will be 5 flip-flops. If I have to store 3 in this, I will simply write 0, 0, 1, 1, 1. So in practical, we don't write 1 and 0 on this at this flip-flop. What is the 0? 0 is nothing, it's a 0 voltage. 1 is what? 1 is sometime earlier it was a 5 voltage. Now I think it has changed some I don't know exact value, but there may be possibility that due to some embedded device we see in the mobile, it is 3 voltage or 0.5 voltage something, and 0 is some different voltage. So we supply this voltage on this flip-flop. So you can see the architecture of a small flip-flop. Okay, this is a basically electronic circuit. If we supply some 5 voltage on this, we will say it's 1, or else it is 0. If you see what is happening at the physical level, so let's say there is a one electron in this orbit, and I want to, so you can say if I am not supplying any voltage in this, it is represented by 0. But if I supply some voltage or some frequency wavelength on this, it will go on a higher state and it will lie in this state. So this orbit you can say 0, and if electron is lying in this orbit, it's 1. So in actual classical computing, this phenomenon is used. We supply 5 voltage, it go in a higher state, and that higher state is saved in this, and we say it as a 1. Now, you can see the same thing which I have discussed here. Now, but there is a possibility that electron may lie between this 0 and 1 also. So if electron is lying between this 0 and 1 also, so it's mean that it may be in the, let's say if it is more towards 0, so let's say if you calculate or you measure this thing, let's say as a 1 meter or whatever, okay, I really, this should not be a good parameter, but just for understanding. And if electron is at this point, 0.3, we are starting from 0 to 1 here. So it is more towards the 0 state. If it is lying at this state, so it's more towards 1 state. But when you observe any electron, you never find this electron at this place. This is a quality, or this is a you can say a characteristic of quantum physics, that whenever you will see either electron you will find in this state, or either you will electron find in this state. but in actually it may reside in between this. So there is a very famous example of Schrödinger cat. They put this cat in some box, and the probability of that cat being found in this box will be live or dead. So there is only one possibility, 1 or 0. But there may be possibility she may be in between that state. So same thing is there in quantum physics. Whenever you measure the thing, whenever you try to see the things, it always found in the 0 state or 1 state, not any intermediate state. So if something, if in last lecture you have also studied the same thing, but in actual, let's say this is nucleus structure of some metal or something. If electron is in between state of these two, so it may be in 0 state and 1 state simultaneously. So this electron, if it is in between the both state, we don't represent it as a 0 and 1, but we say it is with some probability in 0 state and with some probability 1 state, or you can say some coefficient. Now I have written a different notation, so don't get confused. You can say in, let's say, 0 or some beta 1. What is this? We will understand why we write this. And the combination of this can be represented by any symbol, let's say X. There is no need to write this psi or generally terminology used. So this may be a equation of this electron. In quantum physics, we study only this stage, either ground state or excited state. Or you can say 0 or 1. But what about if electron at this stage? So many people have attended last lectures. So if any electron which was earlier here, let's say E0, has reached this at the third stage, in between the orbit 1 and 2. So till now, in quantum computing, we don't study about this. It have more capability to represent electron in which state. We only study whatever operation in the quantum physics we study or quantum computing we study only about this ground state and the upper state, the excited state. We don't talk about the 3-level or 4-level system. We only talk about the 2-level system, which is similar to the classical computing. The difference thing is only here that we assume that electron may be in between this position also. However, there is some methodology through which, by keeping some temperature at -276 or something, we can keep this electron in between this 0 and 1. And in this way, we can create a qubit. However, there is a different way to create a qubit, or to fix this electron at a particular position. But in the actual quantum computing, it is generally done by this by decreasing the temperature at a particular level and fixing it at a particular position. So, as I have discussed, that if we supply some energy on this ground level electron, then it will go in a higher state, and there is possibility that it may lie in between the 0 and 1. So if it is lying in between 0 and 1, then its state can be written like this. generally the terminology used in classical computer as a bit, that is 0 and 1. But in quantum computing, it is called as a qubit. And it is in superposition or in the combination of two probability. So think about it. So as I told, that quantum computing has two characteristics. First is superposition. Superposition means electron is lying in the both state, 0 and 1 state. So if I'm again giving an example, if a person is present at the both position with some probability, so he can work parallelly at the two different location. So if one qubit we are using, that can explore, one qubit can explore two position. But if we take two qubit, it will explore four positions. If we take 3 qubit, it will explore 2 to the power 3 position. So similarly, the classical bit can represent only one position. Here, one qubit can represent two positions. So you can understand in how many less qubit we can complete a particular work with the quantum computing. So we can see from here also, a bit may lie in the 0 state and 1 state, but qubit may lie in the both the state, in 0 and 1. Try to understand this thing with this example. So if I say, write a program that this mouse leads to this cheese, how you will write the program, how your classical computer program will work. Yes, any participant? If you have to access this cheese from this place, or this mouse has to access this cheese, if you have to write a program, how your classical computer will work? Not our. Yes, please, anyone. So generally, this classical computer will try to find some particular path and try to access the cheese. If it is stopped, I will write an algorithm to access this cheese, and if I found some boundary there, then I will stop working.
So now somebody, some participant has written using backtracking.
Yes, so we will have to come again back, and I have to choose another path. If I am not success, then I will again come back and try. So let's say from here, some 5 number of ways are there. So you have to run this program for 5 number of time. But what if we have at the same time, if you apply 5 computer, there is 5 path, and you apply 5 computer, and they all trace a different path. So earlier, let's say in exploring one path, 1 minute is required. So total 5 minutes will be required if I'm using one computer. But if I'm using 5 computer, then total I will require 1 minute to get this cheese. To solve this problem parallelly, we require parallel processing. But in quantum computing, you can represent this solution with some number of qubits, and parallelly you can execute. So only one system can execute this program. Surely it won't require 1 minute. It won't take 1 minute. It will take more than 1 minute, but surely it will take less than 5 minutes. So this is a benefit of quantum computing. Because of superposition, we can represent more than one position at a time. We can run it parallelly. The same concept can be used to solve the traveling salesman problem also. This you have idea because the previous speakers has discussed about this thing. I think the factorization of number, which is generally the key concept of information security. So if you write a program to find a factor of 72, it is easy to or hardly it will take some 5 seconds or something second, it will give the number of factor of this. But if you take a very big number, then see in how many times your C program or your Python program find number of factor. Let's say the length of that number is 10 or 12. It will take huge time. So the main idea of this encryption, I'm discussing very briefly about this. I'm not going very inside about this encryption thing. RSA algorithm. So RSA algorithm use this concept and try to encrypt the data using some prime number factors. And to decrypt this key, we need these prime number factors. If you read this fact, the length of RSA key, the encryption strength depend on the size of key. The encryption strength increase exponentially, typically 1024 or 204 bits long. But experts think that 204 is better than 1024 because it takes a lot of time to break the key. A 256 private key will have this 78 digit. No supercomputer on this earth can crack this in a reasonable time frame. But so there is some figure is given that 2048-bit RSA key would require 6.4 quadrillion year to calculate or to break by the fastest computer. But in quantum computing, it will take only 8 hours with the use of 20 million qubits. So earlier it was somebody has reported that we required 1 billion qubits. It's around, I think, 100 crore qubits. But you can break it. There is a statement by Google, Greg, that you can crack this in 8 hours with 20 million qubits. However, there is no need to worry because till now, I think we have 156 or very less qubit computer. Okay, but this algorithm came in the year of 1996, which talk about that we can find the factor of a very big number also in very less number of time. Now, second property is entanglement. So basically, this property is mainly used for using first property that a qubit can be in superposition in the both state. We can do the parallel processing kind of thing or with one computer. And with the second property, that is the entanglement. And this phenomena said that if we have two electrons, let's say electron 1 and electron 2, if we entangle them, or you can say mix them. Okay, so we mix them, it won't become a E3. The electron will be even E2 only. But by entangling them, they have some bond, which is invisible bond. And this bond, if behave in such a way that if you perform some operation on E1, let's say you have mixed this thing and you have separated out this electron E1 and E2, let's say 50 meters apart after entanglement, or you can say mixing E1 and E2. And let's say this rotation of electron is on upward direction, or you can say, so basically when you see these orbits, so electron move in the circular way around this nucleus, and they also have their axis, they rotate about their axis also. So sometime I don't know exactly, the clockwise is considered as upwards and the anti-clockwise is considered as a downward. Okay, so let's say one electron E1 is moving in upward direction or clockwise direction, and if you change its position or its motion, then at the same time that you find the changes at the E2 also. So you may think that they may have some magnetic force or something which is forcing him to behave in the same manner or some different manner as we are performing some operation on E1. But rather than 50 meter, if you separate out it 500 kilometer, surely no force, magnetic force will work at this distance. At this distance also, if you perform some operation on E1, at the same time, you will see the changes in E2. The experiment has been done that one electron is, after entanglement, they kept on one island, and second electron they bring at the second island. And they were very much far about that. And they found if we are performing some operation on E1, at the same time, the operation on E2 is performed. And the reaction time was faster than the speed of light. This was strange. So there is one experiment done by China by using this property. So this is a way, different way through which we find the entanglement. This is if we pass to electron a particular laser beam, so the electron can be entangled by some mechanism, or it can be entangled by accidentally also. But we need to find out which electron are entangled. So this is one of the way through which we find entangled electrons or photons, you can say, because in quantum computing, we talk about these tiny particles. It is not compulsory that we always talk about this electron also. It may be electron, photons, or any tiny thing.
Sir, I have a query, like
Yes.
how this entanglement is attained when we have to do certain tasks, like we are using quantum computing for certain kind of applications for solving the problems. How this, like if it is happening as a matter of chance, like by itself, it may be there, but explicitly when it is supposed to be done, then how
Yes,
it is being attained?
So, ma'am, in this, this is a one crystal. If we pass electron through this particular kind of crystal is this, we find the entangled pair. So this is one of the way. Intentionally, we want to find out entangled pair. This is one of the way. There is some more way through which we can find the entangled pair. But this entangled pair we find in the physics lab. It is not possible in computing lab.
Okay.
Yeah.
So that means we will be passing the two electrons which we want to entangle.
Yes, yes. So some kind of they have set up through which they find the entangle. They pass two beams on a particular cluster, and they find this entangled pair. So
what is it you are explaining that they are on the two islands and they are like the change is made and with more than the speed of the light. So any kind of reasoning has been developed, like why it is happening?
Ma'am, still they did nobody found that why it's happening and how it's happening.
Yeah.
But they know this is happening, and using this feature they are using in communication. So in 2016, yes. So in 2016, they have done one experiment. The China has done experiment that they bring one entangled qubit on satellite, and one qubit at their station. They made changes on this station qubit, and they found there at the same time there was a change on this another qubit also. So, but that change happened. You need to communicate through classical channel only. So you can. This is a problem till now we have that to, let's say if I want to send some message, some secret message through this electron to at a particular station E2, or some, let's say some station 1 to station 2. And I have this entangled pair, electron 1, electron 2, and let's say there is some combination of that. Let's say I want to send some number, some key to at station 2 to open something, and I have pair of these electron, I will say E1. If I, let's say this position is like this. If I want to send some number, let's say I want to send 3. So what I will do, I will change its position as upward. And how they have entangled, so see, in the same way, it will find that we got 3 here at the same time without any delay. But this, we got 3 here, or we got this qubit has flipped in this way. This message has to be conveyed through classical channel only. But this is happening, how it's happening, it's still under research. So, and one more thing is that whatever I'm sending, it cannot be encrypted. So there is a no cloning theorem, which we will not study here. I think some lecturer has covered it. Shikha, some lecturer has covered
it? Yeah, it was covered, no cloning.
So if we try to copy this thing in between, it is not possible to copy. Because you will find, if you try to copy it, so it will destroy the message. Whatever you will get, it won't be the same as whatever you have sent. Because when you have observed this, this position or the state change.
See, like just now you said, like when we make a change in the electron 1, the change in the electron 2 is made automatically.
Yes,
right?
Yes.
Right. But like what information like we are communicating via the classical channel, like
so ma'am, we have the classical channel. We are saying that let's say here I am sitting and I am saying I'm changing something, and at the station 2 you are sitting and you have found that it's a 3. Now to confirm that that I have made here 3, you will call me.
Okay.
So
Okay.
this,
that kind, like we are just confirming that
yes.
this change has happened due to electron 1 or
yes.
Okay.
So this confirmation is done through classical.
Yeah. Okay.
So many army organization or security organization are using this quantum communication for the secure communication. India has the DRDO has done this experiment for the distance of 27 kilometers till now, and still they are working on this. I think Professor Anirudh Pathak from JP University may better know about the progress of this. He is a key person in this quantum encryption security. Sir ka talk ho gaya, madam?
Sir, he had a talk yesterday.
Okay, fine. So in 1.5 hours, it's difficult to tell everything. So this is a world first quantum entangled photo. Okay, I don't know much more about it, but I found it on internet, so I'm just sharing this. So we understood the 2 properties of quantum bit. First is entanglement and second is superposition, and both the properties used in a different way to for the different applications. Now we moved a little bit towards how this quantum computing concept is utilized to solve some classical problem, and how this inspired algorithm is we have proposed. So as This electron in this state, we say it's a 0. Electron in this state, we say 1. But if electron in between, we say it is with some probability or some coefficient in 0 state and 1 state. Let's say its coefficient can be A and B. Fine. Now, in actual quantum computing, it is generally represented by a qubit, and qubit is represented by 2 state. This, rather than simple bracket notation, this notation we generally use in mathematics, they use a different notation. So rather than having simple 0, it is basically a matrix having this value. Thank you. And here is some coefficient we have used. So this is saying the probability of that qubit in 0 state and then 1 state. You will see many matrix operations in quantum computing. This is just a basic of a single qubit, how a qubit is defined and how this matrix is represented. So you can see this is basically a bracket notation. So a qubit can be defined with this probability coefficient, and there is some rule that the summation of this probability, generally it's happened, should be 1. If you go in detail how this come, so if I have to find an electron in with what probability in 0 state, so I will write basically it's not correct way. So this is basically an inner product. When you want to measure a qubit in what is the probability in 0 state, I just multiply with the 0 state. And if you expand, so when you calculate, it's a generally mod of this, mod of square of this. So if you expand this, so there is a 2 kind of product in the quantum computing. First is called inner product and second is outer product. And the third is the tensor product. So first we will discuss about this product so that you will understand the terminology, why it's happening. So inner product it's mean if I am writing this 0 in this condition, it is 1 and 0. This is a cat notation. Its brand notation will be this, and this will be a complex conjugate of this. Now, complex conjugate and transfer, you can say transpose of complex conjugate. So when you do it, it will become 1 and 0. Now you don't see any complex numbers in here. So we take one example in which some complex number is there. So let's say some A is defined as 1 and 5i. So if you, this is a, let's say generally it will be okay, let me change because I. So if I write it Bra notation, so it will be complex conjugate. So when it will be complex conjugate, this I will become minus I, and then transpose. So it will become, the column will become row, and it will become. So as here you can see, we don't have any complex number, so you are not able to see the exact operation, but this is a complex conjugate operations. Okay, so if you perform this operation, 0 bracket or inner product, so you will find if you multiply this, you will get 1. If you do inner product of 0 and 1, you will find 0. So when you measure probability of any qubit in 0 state, this term will be 0, this will be 1, and you will get alpha square. So to find the probability of qubit in 0 state will be alpha square. Similarly, the find the probability of qubit in 1 state will be beta square. And we know the sum of probability is always 1. Sorry, this is alpha. From there, here we got this relationship. Fine. So this is basically 1 qubit. We can have more than 1 qubit also. If we take operation of 2 qubits, so how it is taken? I want to repeat this thing again. If you are attending this any quantum computing workshop or any lecture series, if you don't have mathematical background, or if you are just like most of them like us who are belongs to computer science field, it is always difficult to understand quantum computing in once. You can keep something from a particular lecture, and while reading the book or whatever content, you can link the thing. But a person who belongs to physics, it's easy to link the things because he has done many mathematical operation on this quantum physics. So if you think that you will learn first quantum physics, you will attend some quantum physics lecture, then you will easily understand quantum computing. So this is a good way, no doubt, because you can visualize the thing, but you can visualize till a particular extent. After that, the mathematics come. But it is not very much compulsory that you have to learn quantum physics. Without learning quantum physics, you can do the quantum computing also. But it is always good to have some basic knowledge of quantum physics. So such kind of this bracket notation, which you are listening first time, you may have experience there if you have studied that. So you have seen the dot product, sorry, not dot, inner product. Now the outer product. So when you multiply this, it will become 1, 0, 0, 0. The result of outer product will be a matrix, but the result of inner product will be a number because we are used in that in measurement. Now we have seen the single qubit operation till now. Now, for example, you have a system in which you are dealing with more than one qubit. Let's say electron 1, electron 2, they are something here. So how to combine this? How to deal with 2 electrons or more than 2 electrons or 3 electrons? So to deal with 2 electron, 3 electron, there is a terminology we use of tensor product. So for example, if you have one qubit alpha 1 0 plus beta 1 1, if you open this in the, you write in the matrix form, it will be alpha 1 0 plus 0 beta 1. If you write in combined form, it will be alpha 1 beta 1. So I'm writing equation for one electron. Let's say this is my psi 1 and this is my psi 2. Similarly, if so, these are the simple probability how much they are belongs to state 0 and 1. There is a psi 2, also have some parameter alpha 2 and beta 2 probability. Okay, I am not writing in this form, I am directly writing in this form. So these are the qubits. Now, if you have to perform some operation on these 2 qubits, you need to merge these 2 qubits. So to perform operation 2 qubit, you require a tensor product of this. Now, tensor product result, you see how the tensor product is done. So basically, the tensor product is done in this way. Alpha 2 beta 2. So if you see the result, it will become alpha 1, alpha 2, alpha 2, beta 1, beta 2, alpha 1, beta 2, beta 1. So again, you will find a vector. This is a tensor product. If you see in actual, so what is electron? Electron is a basically having dual property. It sometimes it behave like a wave and sometimes it behave like a electron or some particle. So what we are doing, we are writing in this equation, it's mean we are representing this electron in the form of vector. Similarly, the psi 2 we are writing, psi 2 is alpha 2 0 plus beta 2 1. We are writing in the form of some equation. When we merge two, so or you can say in the form of vector. So when we merge two vector, we found another vector. So you have seen in inner product is a way to measure a qubit or to see, or you can see it's like eye of us to find qubit lie in which state. So to measure the qubit, obviously to if we are measuring something, we want some discrete number at the result. So here we are finding the discrete number after the inner product. So it is used for only measurement. But the tensor product is used to merge two qubit and make a different vector. So if you want to perform some operation, so there is some question. So want to perform some operation, then you need to make a third wave using this psi1 and psi2. And this third wave again will be in the form of vector. So when you see such kind of equation, we easily understand this. This is a 1 qubit. But in 2 qubit, how we got this and how we write this, you can understand with the example here. Let's say this alpha 1, 0 plus beta 1, 1 is here. Alpha 2, 0 plus beta 2, 1 is here. So here I will write alpha 1, alpha 2. Alpha 1, beta 2. Beta 1, alpha 2. Beta 1, beta 2. If you see this alpha 1, alpha 2, and if you expand this matrix 1, 0, 1, 0, similarly alpha 1, beta 2, this is 1, 0, and this is 0, 1. Beta 1, alpha 2, this is 0, 1, and 1, 0, plus beta 1, beta 2, this is 0, 1, and 0, 1. If you do the same kind of operation, you have to multiply alpha 2 with alpha 1, beta 1, and beta 2 with alpha 1, beta 2. So see what matrix you will get. Alpha 1, alpha 2. You will multiply 1 with this, you will get 1, 0, and 0 with 0, 0, 0. Alpha 1, beta 2, you will get 0, 0, then 1, 0. Beta 1, alpha 2. So again, you are getting some metric or some vector which is representing some wave in the this electronic space.
In the second one, it will be 0, 1 and 0, 0.
Ma'am, 0,
This
0.
one, alpha 1, beta 2. First,
Yes.
we will multiply by 1. We
Yes,
will get
so 1.
0, 1. Isn't it?
So, ma'am, first we multiply 0 with 1. It will be 0. Then 0 with 0, 0.
Then
1 with 1, 1. 1 with 0, 0.
okay.
So we will replace this thing. So it will look like in sequence. So it will be 0, 1, 0, 0. Beta 1, beta 2. It will be 0, 0, 0, 1. So in the bracket notation, you will write this term as a 0, 0. Now this term, as if it should be in sequence, so this term will be written as 0, 1. This term written as 1, 0, and this is as a 1, 1.
Not change the order here, no?
Yeah, I did not change order. So basically, it should be ideally we write in this way 0, 0, 0, 1, 1, 0, 1, 1. Yeah. So
changing the order will change the vectors also.
So no, we can. This is simple plus operation, so we can.
No, here this tensor product.
So order as if I expand it, it will be 0, 1, 0, 1, 1, 0. So I will get the same. I did
0,
not get
0.
Yeah, 0, 0, 1, 0.
1, 0. But so if we change the order of this product, the output will be changing. No, output vector will change.
Yeah, it may little bit change in the case. So it's a unit vector, so we won't find much difference. If let's say we do here only 0, if we are doing this, then we will get 0, 1, 0, 0. If we change this.
That's what I'm saying.
So fine, I have done in sequence.
No, that's fine. Just
Yes,
that
fine.
was just
Okay.
to understand the thing.
Beta 1 alpha 2 plus beta 1 beta 2. So from here we got this equation. So alpha 1 alpha 2 is probability that bits in the 0 0 state. So now we are with 2 qubit, we are representing 4 positions, 2 to power 2. So this is a number 0.707. It's nothing, it's a 1 by root 2. It's a 0.5. So when you square it, you will get this. So consider a 3-bit qubit register. In the same fashion, you can do the operation with 3 qubit. You have to multiply this qubit and you will get some probability sequence of in this way. So it's a little bit resemble with the classical computing with the number 000111. Any doubt till here? Fine. Now, to perform some operation on this, for example, in classical computer, we have RAM, and on RAM, we want to add 2 numbers. Let's say my RAM is just 3-bit width. So my number is, let's say, I want to add 1 and 1. So 1 can be written in 001 way. And in the second position, there is again 1, or you can say 2. So I want to add 1 and 2. So what I will do, I have to perform some operation, or let's say I want to just flip this bits. So to flip this bit, what gate you use? You use NOT gate. So in this flip, the operation will be 110. Correct? So what you are doing basically, you are supplying one. When you performing this operation, you are changing 1, means you are, if you see the atomic structure of this, the electron was in the ground state. You have supplied some voltage on this, so it reached to higher state. This is physical meaning of this. So gate are used basically to perform some operation on this electron, so that we can change its position or change its actual value, so that we can get some desirable result. So similarly, in quantum computing also, if we have electron in between these 2 orbits, we will supply something on this, some photon on this, and we will see the changes on this. So basically the gate operation, I think there was one lecture on classical and quantum gate by one renowned speaker. Yes. So he has also discussed the same. So this gate, whatever the gate you study in the classical computing, AND gate, OR gate, XOR gate, so basically they are changing the state of electron by supplying some voltage. But in copy, we don't see this voltage difference. We just change 1 and 0, 0 and 1. Similarly, in the quantum computing also, to perform some operation, to perform some addition operation, subtraction operation, or some operation, we require gate. But the gate are a little bit different here. The quality of this gate are that whatever result you find in quantum computing, for example, let's say you have to do OR operation. So you will get 0, 1, 1, 1. Now somebody has told you that this is your x1, x2. Let's say this is result. Somebody told you that you have applied a OR gate and your result is 1. So can you predict the value of x1 and x2 bit? So you will say there is a one chance that it will be 1, 1. Okay, both are equal. Now, can you predict that there is also a chance that it can be 0, 1? So can you exactly tell, or can you exactly get the reversal value from which you got the result? In classical computer, it is not possible. But in quantum computing, you can get the input from the output. And because of this reversibility, you save a lot of energy, which we will discuss in the PPT. So this is a generally classical gate, AND gate. You are aware about it and you have studied about this. We are applying AND gate operation on 3 qubits. Now this is OR gate on 3 bits, sorry, not qubits. Now you have heard about the NOT gate also. In NOT gate, make 0 to 1 in the classical bit. In place of NOT gate, we have a gate in quantum computing called as X gate, which work equal to the NOT gate. Now everything is done here by matrix operation. So you can see I am applying this NOT gate on 0 state and I am getting 1 state. So again, try to understand this matrix is just a representation to for understanding of actual phenomena happening on the physical world. But in actual physical, if you visualize, you have supplied some photon, some frequency photon on this qubit. So it has changed to in the state 1. I was talking about reversibility. So see how we can get the result. However, in the NOT gate, in the classical computing also, if you got 1, it means your input will be 0. If you got 0, surely it will be 1. So it won't be a good example if I explain with the help of X gate. There is some more gate. For example, a bit, electron bit, or sorry, electron is in ground state or 0 state. This is 1 state, and I want to bring it in between this in the superposition state. So it's mean I want to supply, or I want to throw a photon of such energy so that it reaches to in the superposition state. So this operation, the mathematical representation of operation, is done by Hadamard gate. So Hadamard gate help to bring qubit in the superposition state. Now we will try to understand how we get the actual qubit back from the result. So I write 1 by root 2, 1, 1, 1 minus 1. Now I have applied this gate on 0. So it will be 1 by root 2. This will be 1. This is 1. One by root 2. I can write in this way also. If I take this in the bracket notation, it will be 1 by root 2, 1. These are the probability parameter. So the probability of qubit in 0 state is alpha square. So it will be 1 by root 2 square. That will be half. Similarly, this will be half. So mean by applying Hadamard gate, we brought this zero state qubit in a superposition state with equal probability. Now, I apply this 1/2, 1, 1. So your answer will be 1/2. If you multiply, it will be 2, 0. So whatever result we got, we again apply Hadamard gate on this, and we found that we got the actual qubit from which we got this superposition state. So it's mean we can get input from the output state. And this example explained that the quantum gates are reversible. However, except the NOT gate, there is one more gate in classical computing. I don't remember exactly the name of it, that also act as a reversible gate. Because I don't want to tell anything, you have already listened many good speaker who belongs to physics area and core quantum computing area. I just try to learn few things from, as my background is also computer, so there may possibility something I may be saying which is not exactly correct. Okay, if something is there, please correct me. Something you find, please correct me. So to represent this qubit on graph, generally we use Bloss sphere. So Bloss sphere, you can see this is a Bloss sphere. So this is a zero. This, when I'm writing zero state, this is a zero state. When I apply this Hadamard gate on this, it comes in superposition state of 0 and 1. So with 1/2 half possibility, it is in 0 state, and half possibility in 1 state when you measure this. So this Bloss sphere is a good representation of a qubit when you perform operation on a single qubit. But when you go on the multiple qubit level, so sometimes it is very difficult to draw these vectors on this Bloss sphere. Any doubt till here? So these are the few gates. As you have studied the gates in the previous before 2-3 days, so I won't discuss each gate. So this is a gate we will utilize in when we understand the quantum key mean algorithm. So this is an operation I have done, reversibility example by X gate and Hadamard gate. Okay, so X gate it's very easy, but Hadamard gate, you can see I applied Hadamard gate on this, whatever the result I got in the superposition, I got 0. Similarly, when you apply Hadamard gate on 1 qubit, you will get this result. And again, you will apply Hadamard gate on this, you will get the original qubit. Now, loss due to irreversibility. If you are not able to get input from the output, then what will happen? So everybody is aware about the Moore's law. We say that the number of transistors per silicon chip will double in every year. So earlier, you can see the first computer size. Later on, this is our first computer size. Later on, we see that we can keep our laptop not on just our lap, but on our palm also. So you can see how the size is decreasing. So when size is decreasing, so on per square feet or in a particular region, the number of chips are increasing exponentially. When the number of chips will increase exponentially, so you can understand in one particular point how much heat will be generated. So if that heat will surely degrade the performance of computer. So this is a figure in which it is told that how many number of, or the progress about this is till 2025. How many number of neurons or electrons per square feet in your computer. So if you see this 190, it's better to see some IBM 70 computer. So this is zero reference. Better you see Pentium 3, Pentium 4. I think few of you aware about it. So in 2005, this is a Pentium 4. And here you can see on the y-axis, the number of calculation per second, the number of chipset required is attached on this. Similarly, when we go exponentially, so it will increase exponentially. So problem in future will be, we will have to find the integrated circuit which measure on atomic scale. As more logic element into smaller and smaller volume and clock them in higher frequency. So energy cost money. So portable system exhausts their batteries. So just like our mobile phone and several watches will require a lot of battery, and because of this, many more number of chip in a small area, system will overheat. So if you see this figure, when computing system erase a bit of information, so what you have to do, whatever result come, you will have to delete from memory. So when you delete something from memory, then 2 kT of energy you have to dissipate in the environment. So if you want to save this heat transformation or heat or the energy required for deletion of any number, we need to reverse the qubit so that we can get the same input and we can utilize further. So this reversible operation can help us into getting to reduce the heat erased by, or the heat by these chipsets. Now there is some more gates are
Can
there.
you just repeat the that you explained that how we are able to save energy when the bits are operations are reversible?
So, ma'am, for example, if I have add 2 plus 2,
right,
I have to get the result 4. So in computing in memory, I will write 4. Let's say 1 plus 2 I have added. So I will write this in memory in this way, 1 1 1. Now, if I am able, and these are the two position, let's say x1 and x2. This is y1. This is 0 0 1 and 0. I have added 2 and 1.
Yeah.
Okay, let's say. So if I'm adding x1, x2, I will get y1.
Right.
This is 1, 2, 3. Now, if I have to utilize this space, I will have to delete this.
Right.
This stored data. While deleting this, storing the stored data, this much energy released.
Okay.
But if I need not to delete it, if I have to just reverse back the thing which I got from the output, then it is easy to consume this.
Okay.
Yeah, we can reuse these qubits.
Okay, okay.
Yeah. So where we are now, this is a quantum computing work, or you can say quantum computer by Google. You can see Sundar Pichai sir is here. IBM also doing a lot of work. In India, the status of quantum computing, India is also making a quantum computer. As per my knowledge, there may be possibility that things has been changed. There is an institute, Tata Institute of Fundamental Research in Mumbai. Yeah. Just, I reserve this for talk. I don't know. Please, you can engage some classroom. So in India, there is a Tata Institute of Fundamental Research where we are building some quantum computer, and this is a status of our quantum computer. I think this is a very old picture. Now there is some progress there. So this was some basic about quantum computing and where we are now. Now I will discuss about this quantum evolutionary algorithm and quantum K-mean algorithm. So ma'am, it's should we take some break, or we can because I think it will require more than 1.5 hours required for both the things.
Participants, do you need break or shall we continue? Sir, आप बताइएगा.
नहीं, जैसे 11:30 तक एक लेक्चर था.
हाँ जी, हाँ जी.
11:30. तो अभी ले सकते हैं कि बीच में हम
10 minutes का ब्रेक रख दें हम.
चलिए मैं थोड़ा कंटिन्यू करता हूँ. मैं 20 मिनट का ब्रेक देता हूँ. तो अभी तो मैं थोड़ा कंटिन्यू करता हूँ इसी को.
हाँ जी. Okay.
So as in initial, I have discussed this quantum computing thing can be used with a classical computer, that is a quantum inspired algorithm, and second is actual quantum computing, that is a quantum K-mean machine learning. So this is also machine learning, but it is inspired by quantum computing. So here we are explaining the quantum evolutionary algorithm. So how to use this quantum computing concept to making algorithm for classical computer. So these are the few steps through which we can use this quantum computing concept for making algorithm for classical computer. For example, I want to find, about this neural network. In neural network, there is a connection weight. So there is a different algorithm through which we find this connection weight. Or, for example, you take K-means algorithm. So in K-means algorithm, there is several parameters which we have to decide manually. For example, you have to decide initially the number of clusters. How many number of clusters you have to take. So you have some data set of, let's say, 1 lakh sample, and you don't know about the data set. So basically the clustering algorithm find cluster, but you need to define the cluster initially. Let's say K equal to some 10, 100 or whatever. So if you have to find this number of cluster, how many should be there, you need to represent this number of cluster in terms of qubit. After defining this in a qubit, because we are using quantum computing concept to find the how many number of clusters should be there. After this, you use exploration. Exploration mean let's say you have 1000 number of samples, and you are randomly you take quantum cluster the number of cluster in K-means algorithm. So hope everybody is a little bit aware about the K-means. If not, there is no need to worry. I will explain this K-means algorithm here. So initially we have to decide, because we have this data set, and we have to decide in how many groups we have to accommodate these samples. So let's say randomly we decide, let's say 10. We don't know how many will be there, but we have decided 10. But as we have defined 10, even the number of actual cluster or number of the category of data, let's say 50. But as you have defined 10, the whole data will be cluster among this 10 number of cluster only. So this is not accurate way. So we can, so how many number of cluster we can have? So the cluster number can we have from 2 to root n. So minimum number of cluster can be 2, and maximum number of cluster can be root n. So root n means, let's say 1000. So what will be the value of root n? 31, 32, 33, let's say 33. So as there is one research which say the number of cluster you can take from 2 to root n. You can take any number from in between this, it will give you good result. But still we don't know how many number of should be there. Then we have this range of 2 to 33. So first we have defined number of cluster, let's say I define by k in terms of qubit. Now I define a range or area of exploration which I have to find this number. So in any evolutionary algorithm, there's a two important thing is there. First is exploration and second is exploitation. So for exploration, you find some search space. So this is a search space to find number of cluster 2 to 33. After that, we found the search space. We have to find the we have to find optimal value of that parameter, and then we have to apply the exploitation method. So I give one more example. For example, let's say this is a graph of sin x. And you have to find, this is a value of x and this is value of y. You have to find value of x on which you get maximum value of y. So as we are studying since school time, we know that in 0 to 180 at x equal to 90, you will get the maximum value of y. That is 1 sin 90. So if there is some similar problem, you have to find the maximum value of anything, then there is a search space in 0 to 180 you have to find. Now this 0 to 180 I will divide in some small search space, and after defining some small search space, I can see the maxima is here. So I need to come slowly in this search space area. हाँ सर 2 बजे तक बुक किया हाँ 2 बजे खाली. So this exploration and exploitation can be understood with a more better example. Let's say this is a cricket field, okay, and I make this cricket field here. I'm very sorry, my drawing is not very good, but I will try to. And this is a pitch, and there is a one tree, big tree, and in this ground there is a wall, okay, and the height of wall is more than the player who is standing here. There is a one batsman who hit a shot, and this shot crossed the wall and passes this wall, okay. Now there is a tree, so there is a chance that this wall will collide to this tree and may lie in this region. Let's say I say this region is a 1. Now there is a second chance the ball won't collide with this tree and may be possible lie here. This is the second possibility. Third possibility that the ball is collide to a right side or the other side of tree and it may go here. A fourth possibility that it may collide that side and it may go here. So there is four areas there in which the all filter will try to find ball. So let's say 12 players are there who came to find the ball, and they found that these are the four possibilities where ball may go. So they have divided their among themselves in 3-3 team, and they are trying to find this. So to find this search space is called exploration, means where we have to find the things. Now this team, let's say ball has reached this area, okay, in the second area. This team will find for some particular number of time, and they will say the ball is not available here, we have explored all the area. So they will move to this area. So 3 plus 3 all are searching in this area. Now the fourth number team also, this four search space area team also said that the ball is not here, so they will move to this region where a player is still finding the ball. So here again the 3 plus 3 will come. Now this region people say we have explored all, so we will go there. So you have seen these searching persons are moving or converging towards a particular search area. There is a possibility of finding the ball is more. So the process of this is called exploitation, means moving or converging towards a area where there is a more probability of finding the solution is called exploitation. So in any evolutionary algorithm, it should have both a property, the exploration the property, and after that finding exploration area, it should converge towards a area which are towards the solution. So let's say this is a ultimate aim, and these are the different birds, or you can say fish, or as you can see in the this in nature, this there are some birds which used to fly over the sky, and slowly they move to a particular area where the food is available. So they try to explore the area, and slowly they try to converge in an area where food is there. So this is basically nature inspired thing. So hope you have understood the exploration and exploitation both. Now after this I will explain, I will take some break, and then we will discuss about the practical thing about this quantum evolutionary algorithm and quantum K-mean after this. Is it fine, ma'am? Hello? Hello?
Yes, sir. Yes, sir. Om, sir, I'm here only.
Okay, ma'am, I am stopping
Okay,
here.
sir. We will. So participants, we will be having a 10 to 15 minutes break. Sir,
Yes.
we will join. We will be joining at what time? We will be joining at
11:55 or 12.
Okay. So we will be joining by 11:55.
Yes, fine, ma'am.
So we will be having a break for 15 minutes.
So my screen was visible.
Yeah, sir. Your screen is visible.
Okay, still showing the screen. Fine.
Om sir, am I audible to you? Am I audible, Om sir?
पायल अभी सर करेंगे
नहीं,
12
उन्होंने
और 12:05 पर
11:55 बोला था उन्होंने, that's why बस
12
ठीक
नहीं
है,
मुझे मैसेज किया है।
ठीक है।
Good afternoon, everyone.
Good afternoon, sir.
Yeah. Can we start now?
Shall we start? So, participants, the sir has come. Please join. सर आप स्टार्ट कर सकते हैं.
Okay. So we stopped here. We were discussing about exploration and exploitation. So
Yeah.
the explosion can be achieved in quantum computing by using some observation process. If participant from JP University, similar work has been done by Himanshu sir also. I think sir has joined. Sir is also in this participants. So this is a process of exploration in which we take two qubits. Let's say some parameter we need to find x, then we can take 2 qubits or 3 qubits depending upon the search space. I have taken 2 qubits. Let's say the problem I need to solve is y equal to or fx equal to sin x. So let's say this is our sin x 0 to 180. Now I have defined this x in terms of some qubit, let's say q1, q2. Now I take one random variable. So let's say the qubit value I have defined, q1 can be defined as a alpha 1, 0 plus beta 1, 1. Q2 is defined as a alpha 2 0 plus beta 2, 1. This X I have represented as a Q1, Q2. It can be represented only one of the probability of this Q1 and Q2. So I represented it as alpha 1, alpha 2. Let alpha I have decided as a 0.707. It is nothing, it's 1 by root 2. So let's say 0.707, and similarly for 0.707. If I'm using 2 qubits, mean I have divided this search space from 0 to 180 into 4, because from this I will get some number between 1 to 4. So my first search space area is 0 to 45, second is 45 to 90, third is 90 to 135. Now how I get this any search space? So I take help of some random variable which generate random number between 0 and 1. So let's say for this I got 0.36 as in first iteration, and for this I got 0.8. I apply a formula alpha square is less than R, then we will write as a 1 else 0. So when you square it, it will be 0.5. When you square it, it will be 0.5. 0.5 is less than 0.36, no? So here I will take a binary bit collection generated from this equation. So 0.5 is less than R, no? So I will write 0. Now 0.5 is less than 0.8, yes. So I will write 1. Now I will convert this binary string in decimal. So 0, 1, I will convert it into decimal. So this is nothing, it's 1. As if I get 0, 0, so if I convert this binary to decimal, it will get 0. So, but my search space area is 1, 2, 3, 4. So to get this, I will add 1 in this. So I will add 1 in this, I will get 2. So it means from the search space second, 1, 2, 3, 4, from this range 45 to 90, I have to select some value of X on which I have to find fx. So to get the value of this, I would use some Gaussian random generator or whatever, some random generator, which give value of X between 45 to 90. Let's say it gives 60. So my X first iteration in the value of X is 60. So I will check value of fx on 60. So what is the sign 60? Yes, please write in chat. What is the sign 60? It's 1 by root 3 or root 3 by 2. Yes, participant. I think more than 40 participants are there. Anyone can respond.
Root 3 by 2.
Root 3 by 2. So what is the value of root 3 by 2? 1.73 by 2. So it's around 0.8. Correct? So in first iteration, I got fx equal to 0.8. So I will stop this process. I will repeat this process until I get 1, or I complete my number of iteration which I have defined. So I know 0.8 is not optimal. So I will update this qubits. Earlier, my qubit was alpha 1, alpha 2. I add 1 here also. It shows the generation. Now I will generate alpha 1, alpha 2 for second iteration. How I generate? So there is a quantum rotation gate. This process I have discussed. There is a quantum rotation gate. So earlier this was my alpha 1 and beta 1. Now I update this by alpha 2 and alpha dash and beta dash. This is a new value. So this is done using quantum rotation gate. G stands for generation. So I apply this formula, and using this formula, I will get some new value. Here delta theta value I take from a small range so that my maxima should not skip. So generally the value can be taken from 0.1 to 0.05. And let's say after updation, I got value of alpha 2 and alpha 1, alpha 2 as a 0.5 and 0.8. Now again the random number will generate some number, and again I will apply the process and I will get the value of some x. Now let's say this time x I got as a between 90 to 135, let's say 120. So I will try to find the value of 120 of sin x, sin 120, and compare the result. And after comparing the result, my qubit will move in such a direction that it will give result in this range. So this we have coded. I want to run this program. I want to show you this program for the sin x, how things work. So I am working with my one student. I think he's here also, Siddharth, who has coded this for demonstrate that how this small process for sin x work. However, sin x is not a big problem because there is only one maxima. There is several problems on which we have worked. There is a multiple maxima and minima are there. So let me run this code. So this is a code for which we are doing for sin x. We have defined 4 such space area: 0 to 45, 46 to 90, 91 to 135, and 136 to 180. And let's say in the initial, the number of iteration I have taken 20. So let's take 10. So in 10 number of iteration, what value we achieve, we'll see. So in the first iteration, as I got 0.8, here I got 0.45. Now this qubit will update, and the last value I got as a 0.98, which is very close to 1. I increase the number of iteration. Let me increase by 30. Let me run this. Now in the 30 iteration, I reached more close, it's 0.99. If I run for more number of time, there is a possibility I will get 1. So let me run for more number of iterations. 100. You can see I am getting 1. So 1 I got in some intermediate state. Let me find this one in. So there may be possibility when you run for 30 number of iteration for multiple time. So we take average result rather than only one iteration. We run for 10 number of times. So you can see in the 45th number of iteration, I got 1. That is a global maxima, or you can say it's only one maxima or in the sin x.
Sir, I have one query. Like here for the sin x, we have considered 2 qubits.
Yes,
so in the real life problem, like when we are using the various data sets, right? Or so using solving the multi-model problems, then how do we decide that how many qubits we should take?
So basically, ma'am, it's depend on the search space length. Okay. So for example, I'll show you 2 papers which we have submitted.
Yeah.
Let's say this single variable.
Yeah.
So here is some mathematical function we have taken. Me and Siddharth and Dr. Neha are author of this paper. So you can see in this graph, there is a multiple maxima.
Right.
So if we draw the graph of this equation, it will be from minus infinite to infinite.
Right.
But to demonstrate it, we have selected some range. Let's say 14.8. So this is a range, minus 15 to 12 we have taken. So this is a sufficient such a space which can be explored by 2 qubits. But so this is a work in which we have taken only one variable. Now there is one more work in which we have taken the multiple variable.
Right.
So these are the equation. This is a 2D graph. You can see there is a multiple maxima and minima are there.
Yeah.
And this is a graph only with respect to 2 dimension. But we have tested for this for 50 number of variables.
Right.
So let's say this is a range, this is a function, shapefile function. It is suggested that global minima is 0 and the range should be taken from 500 to 500.
Right.
So for this, we have tried for more number of qubit. Siddharth, how many qubit we have taken for this? Siddharth is here?
Yes, sir. Sir, we took 8 qubits.
8 qubit for that.
So how do we decide that how many qubits?
So manually we try to increase and we see 100 iteration, 50
Okay,
iteration.
then like we have to just go for the hit and trial and see what is the appropriate value for that.
Yes, gradually we increase.
Okay, fine.
So,
and have you applied to like any of the swarm intelligence then when we are using the various operators that we use in the swarm intelligence for the exploration and the exploitation, then how do we make those updations that we have?
Ma'am, we are working on this. One work is given to one student, which are now implementing the swarm optimization. My turn is not came, so I don't know much more about it, but we will discuss after this.
Okay.
So this is a graph. You can see multiple maxima and minima is there. So let's say take one any function. Let's say fourth function 2 sin x square minus x sin x, whose maxima is 6.64 and minima is, there's a global minima you can see in this range minus 9.84. If we go to the table, this function is 2 sin x square. So you can see we are getting the minima. So we have updated the QA, whatever we are discussing, we have updated it. So we are getting this minima in the 16.2 number of iteration. The maxima we are in 16.4. The things I have discussed, that is a QA, but we have updated this algorithm and found this maxima and minima. Similarly, with respect to this old algorithm, we are getting in the less number of time. So similarly, for this, we are getting very quickly, we are getting that maximum minima. In the another paper, when we increase the number of dimensions, here you can say X and Y, 2 parameter we are optimizing. So you can see the complexity of graph. Here also we are getting a good result, but it's under communication. Let's see what result will come. So this was regarding this quantum evolutionary algorithm. For using this, we have optimized sin x and some other algorithm, other functions also. Now there may be possibility, as I have shown in the paper, there may be functions which having some multiple maxima and minima. In this also this work. Now I will discuss about little bit about clustering. And in the clustering also we have applied this concept. And from this clustering will be basic for you for the quantum K-mean. So clustering is nothing, it's a grouping of unlabeled data. So you can see this is our sample and we have applied some, in this we have applied K-means. So we got 3 clusters. However, the number of cluster, how many number of clusters will be there, we decide prior to the algorithm, before running the algorithm. So we have decided 3. So these all 3 is grouped in all number of sample grouped in this. Now, if you see the clustering, let's say this is a my input sample. The cluster can be based on different parameters. It can select on the basis of color, as we can see the result. It can select on the basis of size. So let's say this is our data set. By color, it has clustered. Now by shape, it has clustered. Now by size, it has clustered. So it's depend what formulation you are applying and how you want the cluster. But generally in K-mean clustering, we use equivalent distance to, or how much our sample is far from our center, we calculate on that basis. So better we understand, okay, this is a general algorithm. So randomly choose K object from D as the initial cluster centroid. So let's say this is my sample, data sample. And this red one, I have chosen as a cluster center. So first I have selected that in my data set, there will be only 3 clusters. Now, as I have selected 3 clusters, so I have to select 3 centers. So 3 centers I have selected randomly, which is under this red circle. The value of this is 3.8, 9.9 for cluster 1, cluster 2 is this, and 3. This is the initial. Now, what we will do with this 3 cluster point, we try to find distance of each point. So let's say this is a point, A2 point, which having value 2.8 and 9.6. We try to find the value of for this, this, and this. So here you can see with the data point 6.8, 12.6, the distance of first cluster is 4, second is 1.1, and third is 5.9. So whichever the closest one, I will say this cluster belongs to that particular, this sample belongs to particular cluster. So the distance from cluster 2 is less. So I will say this data sample belongs to cluster 2. I will try to find distance. I will find distance of all samples with these centers. And on the basis of information of its distance, I will assign cluster number to this. This is a first iteration. In first iteration, there may be possibility that it may not be optimal. So what we will do, we will find mean of data points belongs to a particular cluster. For example, sample 2, 3, 4, 5, 6, 7, and this, and this. This belongs to cluster 1. So what we will do, we will find mean of value of all these and form a new cluster. And from this new cluster, so let's say this is a new cluster and this is a new center point. Earlier it was this, now this is a new cluster point. We will try to find again distance and we will repeat this process until we don't find change in the cluster centers. So this will be our final cluster center and the number of cluster which we have already taken. Now, what is the problem with this clustering, k-mean clustering? If a data set belongs to more than one class, for example, if I have to identify human and animal, so what I have to do, I have to find feature of human and animal. So by some image analysis or by some manual counting, I have found that I have taken few parameters. Leg, so human have 2 legs, while in place of animal have 4. Hand, human have 2, and animal have sometimes 0 and 2. Okay. In case of monkey, we say that there is a 2 hand, but in case of horse, we say 0 hand. Tail, there is no presence of tail in human, and animal there is a 1. So these are the features which distinguish human and animal. But you see the below images. This is an image of a child. So from that image, if I train an algorithm, from image you identify these parameters, leg, hand, all these. So it will categorize this child as an animal. Now you see this picture. It having 2 hands, 2 legs, but there is a 1 tail. So it will categorize this child as an animal. Now you see this. So similarly, there may be many samples which will misclassified because it belongs to, because of this feature, belongs to more than one class. So to solve this, there is a concept of fuzzy, because in life, we cannot say things are always not in crisp nature. For example, if you say 40 degrees Celsius, if temperature is above 40 degrees Celsius, then we say it's hot. But you cannot say 39.99 degrees Celsius is a cool. You can say temperature between 32 or 30 to 40 will be a range of little bit cool, but more cool than hot. So things are fuzzy in nature. Similarly, if you say height a 6-foot person is a long person, but what about 5.11-inch person? It is also tall. It is not short. So, but it is more toward heighted person rather than a short person. So things are crisp in nature. To solve such things, there is a algorithm there is a fuzzy algorithm. Let's say this is a data point which belongs to both the cluster, but in which cluster it has more membership. For example, a person of having height 5.11-inch. It is more close to a tall person cluster. So it will have more membership towards this. So this is this will categorize in the cluster 2 rather than crisp clustering, which will say it come in the range of cluster 1 of short persons. So in real life, we see many data points which belongs to more than one cluster. So to solve this, we apply membership function in this. Data point belongs to which cluster more. According to that, we cluster that, say this, label this data point in a particular cluster. Now, in that we do with the help of fuzzy clustering. But in fuzzy clustering, there is a one parameter which is a fuzzification parameter which say how much overlap should be between two clusters. This is defined by fuzziness parameter. Now, its value is reported in one good paper that it should be between 1.5 to 2.5. But still 1.5 to 2.5, you see, if you take difference of 1, it's a 10 value is there. If you take difference of 0.11, then 100 values are there. So what should be the optimal value? So we have applied quantum computing to find this parameter, or evolutionary quantum computing to find this parameter in this range. So as this is a small range, so we have defined we have taken only 2 qubits. So the range has been defined as a 1.5 to 1.75, 1.76 to 2, 2.1 to 2.25, and 2.26 to 2.5. And based on that, we have formed a neural network and applied this quantum evolution algorithm to form a neural network, optimized neural network, which is able to classify this fuzzy data set also. So this was a brief introduction of quantum evolutionary algorithm. Using it, we are doing some experiment on classical computer. There are many researchers who are working in this area. From JP University, I have seen one paper of Himanshu sir, who applied this quantum evolutionary algorithm in the deep learning. So you can also explore this thing. Now we come to the, hope it is clear. Any question from you? So we have covered this thing with classical computer. Now we will discuss the actual quantum computing or quantum K-mean, which we have to solve using quantum computers only. Any question till now? Fine. So let's discuss quantum K-mean.
Sir, in the previous topic that you were explaining about the fuzzy clustering, so
Yes,
we were you were using the quantum for finding out the degree of you can
Fuzziness.
say degree of fuzziness.
Yes, yes, ma'am.
Okay, okay. So that you can classify whether it is like hot or cold actually.
Yeah. Well, so there was several disease data set in which overlap data are there. So we try to find the correct overlapping between two clusters so that it classify correctly.
So you tested on classification data set for this?
Yes, ma'am. Basically this neural network we found using
Okay. Okay.
So if you see this qubits, which is made of both superposition of qubit in 0 and 1 state. So if I draw the graph of it, so let's say this is this qubit. Now it having some portion on 0, having some portion on 1. So this is called alpha, 0 axis, and this is 1 axis. So in quantum computing, we don't have this data point as a crisp point. Like in classical computing, I define a data set X, let's say data point as a X is a 1.5 and 2.5. In place of a data point, we define always in terms of vectors. So because these are the waves, wave have, so this also can be defined as a vector, but it's compulsory to define this wave as a vector when we do calculation or as a matrix. Now there is a 2 point. So the crux of quantum K-mean is to find distance between 2 points and then assign that data point in a particular cluster according to its distance parameter or distance value. So let's say there is a 2 point x1 and x2. So in classical, you will find the distance 3.5 minus 1.5 square plus 7.5 minus 2.5 square, and you find some value. But in quantum computing, rather than finding equivalent distance in such a way, because we don't have value in quantum computing in such a way, we find projection of one vector. So we will make this as a qubit, psi 1, psi 2, as a qubit, and try to find projection of one vector over other. So let's say there is a problem, it's not going in that origin. And there is a second qubit like this. So rather than finding the distance between these two points, we find how much it is lying over this, how much it is close to this. So this is a one center point, and let's say there is a one another another vector, or you can say another center. Let's say this is it. So if we try to find the projection on this, so you can understand the portion of this projection is more than the, so this is center 1 and center 2. The projection of this vector x or qubit x is more on C1 than C2. So this data point belongs to cluster C1. So this is a basic idea behind the quantum k-mean, rather than finding equivalent distance. So how to do it, we will see. So this is done. So if you make compare with this classical computing, it's nothing. It's a dot product. It's dot product of two vectors. So if you have vector A and vector V, and if you need to find the projection, so you just write A dot B equal to mod of A, mod of B cos theta, and this give amount this value. So the same thing we have to do in quantum computing. Now, how to do this thing? For that, there is a one circuit I am designing, and with the help of the circuit, we will find this dot product. So as earlier I told, there's an inner product, outer product, and tensor product is in the we use this three terminology in the quantum computing. So to get the dot product between two vectors, I'm making one circuit, and step by step I will explain how it's work. So this is my qubit A, and this is my qubit B. I have to find dot product between these two. Now in quantum computing, when you perform any operation on 2 or 3 qubit, or you want to perform some operation on number of qubit, then there is a need of another qubit that is called helping qubit or ancilla qubit, which will, the changes in that qubit will reflect the operation performed on those 2 qubit. For example, I will take here one ancilla qubit or helping qubit, which will tell about how much A is overlapped over B by the value of this ancilla qubit, 0 qubit. So first I will make this circuit, then by step we will understand. It's a sign of measurement. This is a state of qubit after each operation. So as we are taking 3 qubit will merge as I have explained here. When we perform operation on 2 qubit, then we need to perform tensor product on this. So similarly, we are performing operation on 3 qubit, so we will perform tensor product of this 3 qubit. So step 1. So Sin 0 will be written as 0 tensor with A, tensor with B. Now the value of A and B will be anything. Okay. So first the question come in mind that let's say our A and B are 3 and 5, and A is 3 and 5. Let's say this is x1, x2, and B is, let's say, 2 and 1. So how I write in this way? So when you perform operation on quantum computer, first you need to convert your input data set in the form of qubits or in the form of input which quantum computer takes. So there are many methods through which you can convert this in qubit form. I am discussing the easiest method here. Let me take this some number in the range which can be defined by 3 bits. So fine. So if I have to write in binary number 3, I can write 1 1. I have to write 5. What the value of 5 will be? 1 0 1. Correct? How I write 2? That is a 1 0, and 1 as a 0 1. Now you can see difference in this qubit length. So what we will do, we will make equal by padding 0 in this. So my x1 can be represented as 0 1 1 1 0 1. Sorry, the A can be represented as in this way, and B can be represented as 0 1 0 0 0 1. I'm repeating this thing. This is one of the method to convert your classical data into quantum data. There are some many methods. Okay, but this is the easiest way in which we represent. So hope you have understood what is this your A and B, and 0 is nothing. 0 is your 1 0. So you have to take the same value, whatever the length of your A and B, to perform operation. Now this is step 1. In step 2, we have entangled this 0 qubit with A and B. Okay, so we have applied Hadamard gate on this. So what we are doing, we are bringing this electron from 0 state to between 0 and 1. So we are applying Hadamard gate. So we are bringing this qubit on superposition state. So when I apply this gate, so my psi 1, earlier it was psi 0, my psi 1 will be Hadamard gate on 0 qubit. So when I apply Hadamard gate, it will be 1 by root 2 This is my psi 1. Now in step 2, I will apply control swap gate on this A and B. So control swap gate say if my ancilla bit in 0 state, then there is a no change. So basically swap gate, what it does, it swap the value of A and B. And if ancilla bit is 1, then perform swapping. So when you multiply this, it will be a psi 3, 1 by root 2, 0, tensor A, tensor B, plus 1. So when 1 will come, the order will change. As ma'am, you were saying, if we change the order, the bit will change. Yes, So its
Yes,
order
sir.
is important.
Oh,
So you can see the change here. Earlier it was A tensor B. Now after swapping, it's B tensor A. Now in step 3, we will again apply Hadamard gate on this. I think sign 0, 1, it should be 2. Hadamard gate on all this. So I one by root 2 H So when you apply this, the equation will become 1 by root 2, 1 by root 2, 0 plus 1, one by root 2. When you apply Hadamard gate on 1, it will become 0 minus 1. So please you try this operation. So if you let me write this. So it is nothing 1 by root 2, 1, 1, 1 minus 1, and it's a 0, 1. So when you multiply this, it will become 1. See, this will multiply with 0, this will multiply with 1, this will multiply with 0 and then minus 1. So if you expand this, it will become 1, 0 plus 0 minus 1. If you take minus n out, it will become 1, 0 minus 0, 1. So it's nothing, it's 1 by root 2, 0 minus 1. The same thing I have written here, 0 minus 1. If you apply on 0, you will get this plus sign, okay, because it's 1, it will be 1 by 0. So tensor B and tensor A. Now this is my equation. Now I expand this equation and multiply this A and B inside this. So can I remove this? If I expand this, it will become, I take 1 by 2 common. It will be 0 tensor A, tensor B, 1 tensor A, tensor B, plus 0 tensor B, tensor A, minus 1 tensor B, tensor A. I can take common 0 from this and this, and 1 from this and this. So it will be 1 by 2. It will become 0. Plus 1. So this is my sign 3 or equation I will get here. Now I will try to find the probability of my ancilla bit in 0 state. So now I need to find the measurement. So direct way is that just like we write psi equal to alpha 0 plus beta 1. If I have to find a probability of this alpha in this state, so I generally do alpha square. If I have to find the probability of psi in one state, I do beta square. But I also discuss how this come. You need to tensor it, so it will become not tensor, sorry, the inner product. So this will become 0 and this will become 1, and I will ultimately get alpha square. So similarly, when you try to find the probability of bit in 0 state, it will become one by 4. Should I do the same in the same fashion in this equation, or I can directly take this component?
So you can directly take it's fine.
Okay, fine. So if I take this will be my A tensor B plus B square of it. So now I need to perform inner product of in this. So I can write this equation in this way. So there is a one thing you should know. When you find alpha square psi square, or let's say alpha square, so basically alpha square is not just like alpha into alpha in the normal classical computing. In quantum computing, if you find this alpha square, it will be alpha conjugate transport into alpha. Okay, the norms will come in this way. This is in classical, but in quantum, this is a way. So I write this equation 1 by 4. It will have you can see the sign has changed. Now it's a Brand notation. I repeat this thing that the number of operation you are seeing for not some, for it may for many students, it is difficult to understand in the first time. But when you read this again and again, or you will clear your basic, then it will be easy. Still, we are working, but as a computer science student or faculty, we find difficulty to understand the equation and the number of operations it performs.
So can
So
you
there is a
share
note.
some resources from where like all the people from the computer science field would find it easy to learn?
Yes, ma'am, I will share, but even that from one resource, it won't be sufficient because we find something good in one resource and second,
Right.
other things. So I will try to
Yeah.
send some resources.
Sure. Okay.
So when we multiply this, so this will become 1. Again, you will encounter this B. After it will become 1. Similarly, this will become 1. And this will become 1 by 4, 1 plus 2. So if I write this equation, it will become 1 by 2. This is a probability of finding this qubit in 0 state. And this is come in the same form of under root a minus b to whole square. So if my two vector a and b, this is a, let's say b, if they are in the same direction, so if they are same, just like we write a mod a is a 1, if you, or you can say 0 mod 0 inner product 1 0 1 0, that will become 1. So if it will become same, so means these two vectors or two qubits in the same orientation or same cluster. So it will become 1, and the probability of in 0 state will become 1. So what we are doing, we are measuring the ancilla qubit. You can see in the graph what we are doing, we are only measuring the ancilla qubit. So if the probability of this in found after this operation sin 3, if we found that sin 3 in 0 state, it will get probability of 1 in 0 state only when these both are in same direction. If it is in perpendicular, so for example, perpendicular vector we know that is a 1 and 0. So I can write 1 as a 0 1, and this is 1 0. You'll get 0. So if these vectors are perpendicular, means they are not in the same direction. So I will get probability of sin 3 as a half. I can get value 1.2 to 1. So depending on the value between this, I can say these. So I will have sum of all the value, all the vector value between half and 1. So on the basis of this value, I will say that a particular cluster, a particular data point belongs to which cluster. So this is a core of quantum K-mean. So let's say there is a 3 vector, just like we have this A, B, and C, and we were finding the distance of A from B, or let's say rather than B, let's say C1, C2, C3. This is C1, C2, C3. So if we find the projection of A on C1, C2, C3, we will get value between 1/2, in between half and 1. So let's say some value we got as a 0.7, here we 0.6, here we got 0.5 as a half. So it's more projected towards cluster C1. So this is a crux of quantum K-means. This concept can be applied in all the algorithm which required distance measure calculation. We can also write, if we want an exact distance calculation form, we can write in this way also. This is a qubits. Where Z is nothing, it's a so in this way also we can find the distance. But ultimately we have to find the projection, and from projection we can find the distance, and on the basis of distance we can say that a particular data point belongs to which class. So what's the benefit of this? So basically, if you exactly see, we have to do in classical computing, we don't have to prepare the data set. In quantum computing also, we need not to we need to prepare the data set according to qubits. So that complexity we don't consider. Apart from that, it will find the projection. You can see the projection in less number of computation than the finding the equivalent distance. And in this way, it speed up the process of finding clusters. So basically, quantum computing is mainly used to find. Initially, it was, however, there are many benefits, but to speed up the process. So in this way, we can increase the speed. Even that there is some paper which report that they got better accuracy rather than classical computing when they are doing in this way. So this was quantum K-mean algorithm. I hope you understood it little bit. Okay, not fully, because idea of generating this quantum circuit, it is not easy. But if you are good in basic, then you can perform this number of operation, and after performing this operation, you can find the distance of each point and can report the result. Here, rather than finding this, let's say, as I told you, that 0.7 is a membership or the value of A in cluster C1, 0.6 in C2 and 0.5 this here. So rather than based on this, you can also apply Grover search algorithm to find this data point belongs to which cluster. So this will speed up more your process rather than a comparison. So any question? This is my talk, because if I discuss more about this thing, quantum machine learning, so it required discussion of quantum phase estimation algorithm, which find the eigenvalue, eigenvectors, and with the help of eigenvalue and eigenvector, you can solve the SVM algorithm. But it required again 3 to 4 hour discussion, and I'm pretty sure only few will understand because of the I don't know how much basic participant know. Yes, ma'am. Over to you.
It was really a wonderful session, Dr. Om. You explained everything so well, no, and in a very simple manner.
I don't know, ma'am. That's asked to participant whether they got, because the classical part is okay. It is easy to understand, but the quantum part is a little bit difficult.
Yeah, actually, it is difficult and not easy to get everything.
Yes.
Right, but at least now they will be able to start. Right?
Yes.
That is the main purpose of such kind of events, that people who had some kind of hitch in starting with the new topic, now they can start, they know the things, right? So they have a glimpse of each and everything and very deep understanding. But unless, you know, self-study is very important.
Yes, yes. So very good afternoon to all faculty member, Rashmi ma'am, Shruti ma'am, Akansha ma'am, and Himanshu sir. Hope they are
Please
online.
switch on your cameras, everyone. Om sir is there. Please switch on your cameras. We can have a group photo. Everyone, please switch on your cameras for the group photo. All the members, please switch on your cameras. Waiting for the everyone. Please join. Please switch on your cameras.
So some may join on 1:30 because there's no expected time to end this talk.
Ma'am, have you taken the photo? Okay, I'll take. Please, more members, please switch on your cameras.
Priya ma'am is here. Mukesh sir was here.
We all are waiting. Yeah, thank you.
कैमरा नहीं है ना, कॉलेज के कैमरा से वो कर रहे हैं सिस्टम से, तो उधर कैमरा नहीं है, इसलिए प्रॉब्लम है.
Right, right.
There is no camera
This
in
is the
my
best thing
system.
also.
There is no camera.
If participants have any query,
so, ma'am, this is the best thing also, not having camera.
Yeah.
नहीं नहीं, जिसको इंटरेस्ट है वो तो सुनेगा, ऐसा कुछ नहीं है.
नहीं
कैमरा से बोल रहे हैं.
वो एक्सीडेंटली
हिमांशु एक्चुअली काम कर रहा है क्वांटम पे. इसने कुछ पहले न्यूरल नेटवर्क लगा के भी ना एक प्रोजेक्ट वगैरह पे काम किया. मैं उसमें. और सर थैंक यू.
Thank you, ma'am. Thank you for inviting me.
Thank you for being here.
At least we could meet online.
Yeah,
ठीक है.
Yes,
it was really a very nice session, sir.
Yeah. Thank you
for being here. Thank you so much.
Thank you, ma'am.
Okay, sir. Bye.
Okay, ma'am. Bye.
Bye, everyone.
Bye.
So our next session
tomorrow
will
start the session.
We'll have next session tomorrow at 10
Yeah,
a.m.
Shikha?
Yeah. Fine.
Okay, then bye, everyone.